students, now we have come to another experiment in light, right? You can see that. Verifying the length formula and finding the focal length of a convex lens, right? First we will do this for convex lens and then we will see this for concave lens. The above diagram shows how the divergent rays from the object O dash get refracted and form the image I dash when they travel through the lens. Now look at this. If this is my object, I get two rays from that, two divergent rays. The one that goes through the optical center will go straight. Look at that. The one that goes through the optical center goes straight. The other one gets refracted and they become convergent, and at this point they meet again. So this is where you are going to have the image. Image will be real. Why? Both rays, they meet here, right? Because of that you get a real image. But what is this one? Here we have kept the object closer to the lens. Basically we have kept it within the focal length of the lens. When you keep it within the focal length of the lens, what will happen? See, the rays that come out from the lens will not be convergent, that will be divergent. Then you have to extend it back to find the point where they meet. This is where you are getting the image. So when you keep the object within the focal length, the image you get is not real, an imaginary image you are getting, right? And it's larger than the size of the object. So there are two cases, right? One is when you keep the object outside the focal length. One is when you keep within the focal length. When you keep it outside the focal length, you get a real image. Take a note of that. When you keep the object outside the focal length, you get a real image. If u and v are the distances of object and image from the optical center of the lens, according to the lens formula, you know the lens formula, 1 over v minus 1 over u equals 1 over f. The focal length f can be found as follows. If the graph is plotted using the new Cartesian convention, the intercept of the graph of 1 over v against 1 over u will be 1 over f. See, if I rearrange this, it's going to be 1 over v equals 1 over u plus 1 over f. We are going to take 1 over v in the y-axis and 1 over u in the x-axis. So you have y equals mx plus c. Focal length is a constant for a particular given lens. Focal length doesn't change. This is a constant. This is a constant. Y equals mx plus c format of graph you are getting, right? So if you can find the intercept of the graph, the intercept will give you 1 by f. So if you take inverse of the intercept, that has to be the focal length of the lens. To do this experiment, see what apparatus we need. A convex lens mounted on a stand. There will be stand. You can keep the lens on that. Two optical pins fixed with the stand. There are optical pins, right? That is what we use as the objects for the experiment. The meter ruler, a meter ruler to measure the distance, the u and v distances. A background screen. Be careful, this screen is just the background screen. There will be a white color screen. You can keep it just behind all this, the lens, object, behind all of them you will keep the screen. Just to ensure you don't get the interruption of anything behind all this. That means behind this arrangement there might be other objects within the lab. When you look through the lens, you want to get a clear image. You want to get a clear view of the image. Just to ensure the other objects which are not related to this experiment should not disturb, should not interrupt your view, we keep a screen there. There are some other experiments where we keep a screen and on the screen we get the image. Here we are not getting this image on the screen. This screen is used just as a background to ensure we don't get any interruptions. Clear? That's about the apparatus. Point the given convex lens to a distant object and obtain its clear image on a screen. Measure the distance between the lens and the screen using the ruler and find the approximate focal length of the lens. Understand? We can get an approximate focal length of this lens before we go into the rest of the experiment, because knowing the approximate focal length will help us. How do we get the approximate focal length? you look at a distant object in far distance. Why we look at object in far distance? The rays from object in far distance can be assumed to be parallel rays. To get parallel rays, you look at object in far distance. So what will happen when parallel rays reach a convex lens? The one that goes through the optical center will go without any deviation. See, a line like this, a ray like this will become convergent after it passes the lens. Another one will also become convergent. But you know, they all will go through the same point. If this is the primary axis, from the primary axis, if you can find the plane where these the parallel rays where they converge after they pass the lens, where they converge, if you can find this point, then this distance will give you the F. This is what we are trying to do. What you do, you take the parallel rays. So one thing you can do, rather than keeping the parallel rays like this, if you can do like this, if you can keep your lens also tilted so that this middle ray becomes the primary axis for you, it's easy for you to measure the distance. However, get parallel rays falling on the lens and find the point where they converge and get the distance between the focal, the convergent point and the optical center. That will give you approximate focal length of this. Approximate focal length of this lens. That won't be a precise measurement, but you can get an approximate measurement. Do that first. Then draw a straight line in chalk on the table. Midway on this, place the lens mounted on the stand normal to the line. See how we do that. Let's say this is the line you have drawn with the chalk. Somewhere in the middle, you keep the stand and the lens. That's your stand and the lens. Then what do we do? On one side of the lens, at a distance little further than the approximate focal length that was found, place the optical pin O fixed on the stand on the line drawn so that the tip of the optical pin is on the optical axis of the lens. The primary axis or the optical axis, let's say the optical axis is, let's say this is the optical axis. Right. If this is the optical axis, now what you do, keep an optical pin such that the tip of the optical pin is approximately at this line. So what we usually do, we first keep it closer to this and find whether the tip is coming approximately closer to the primary axis or the optical axis. Then we take it away. And where we should keep this, we already found the approximate focal length of this lens, right? Let's say approximate focal length is 10 centimeter. Keep it a little outside 10 centimeter. From here, maybe in 15 centimeter, you can keep it. Why? If you keep it outside the focal length, then only you can expect a real image on the other side. Not a virtual image, you will get the real image. That's what we are trying to do. Keep the object there. This is going to be the object. Place the background screen on the same side as this object pin, but further away from the lens. On the same side, but away from the, at the end basically, at the end. So let's keep it. This will be your background screen. That's a background screen, S. This is O. This is L, lens. Right? S for screen, O for object, L for lens. Place I on the opposite side of the lens. See, on the lens, right side of the lens, you have kept the object. Now, on the left side, you keep your eye and observe whether you can see a clear image of object. It has to be an inverted image. I showed you the ray diagram you see here. It has to be an inverted image. Inverted image. Inverted real image is what you expect to see here. Let's see. Inverted real image is visible. If not, push the object pin further from the lens until the inverted image is visible. What happens? Sometimes if the approximate focal length you found at the beginning, if it is wrong, let's say it was actually 20 centimeter, but by mistake you found it to be 10 centimeter and then you kept it in 15 centimeter. So what is the real focal length? 20 centimeter. But you kept it in 15 centimeter, which means you have kept it within the focal length, right? If you keep it within the focal length, you will not see a real inverted image. Then what you must do? Push this pin further away from the lens to get a real inverted image. Until you see a real inverted image, you adjust this pin. Basically, push it further away from the lens. Place the eye along the line and confirm that the inverted image of O is vertically situated along the line. If it is not, rotate the lens slightly within the stand and adjust it to be correctly normal to the line. Now, there are a couple of errors that you can do here. Right? Sometimes when you do experiments, there are a few errors that can happen here. One, see, if this line is drawn like this, the lens has to be kept perpendicular to this normal, perpendicular to this plane. Sometimes what will happen, the length may not be like this. You might have tilted the length like this. The lens might be in an angle. Lens might be in an angle. It's not actually 90 degree. It's in a different angle. Right? See, to this plane, if this is the line you're talking about, to this plane, lens has to be right perpendicular to that. If it is not perpendicular, then the images will not be aligned in the same line. So that is first problem. Adjust the lens and make sure it is perpendicular. Second point, the pins may not be on the same line. Lens and the pin, the center of the lens and the pin both must be in the same line. Then only you will get the image also on the same line. If they are, that's why we have drawn this line, straight line. Because of these two errors, one is the lens is not perpendicular to the plane. Two, the lens and the object pin are not on the same line. Right? Then if it is not on the same line, that means, see, when you are looking from here, this is point number 1, see point 1, point 2, what we mean by point 2 is the center of this lens, point 3. These three have to be in the same straight line. These three have to be in the same straight line. Otherwise, you will not see them in the same straight line. You will have the object pin here, image here. They will not be in the same straight line. See, they will not be in the same straight line. They will be deviated. One reason why they will be deviated, the lens is not perpendicular. I will show it when I do the experiment. Two, they are not on the same straight line. Clear? So, adjust the lens and make sure you can see. Where is it? Also, if the tip of the pin is not seen at the center of the lens, adjust the place of the lens to be vertical. Now, place the other optical pin along the axis and adjust the tip to be on the principal axis. Adjust P either forwards or backwards until the tip of P coincides with the tip of the image I. Look at this diagram again. So, you will be able to see an inverted image of this pin. Inverted image of this pin. Let's say the image you see is, let's say this is the image you see. Let's say this is the image. You are able to see an inverted image. Now what we are going to do, let's keep another pin on this side. Let's keep another pin on this side. What you can do with this pin, while you are looking along the axis, you shift your eye laterally. That means if you are looking like this, just look. Change your line of observation, line of view, change it. That means move your eye laterally and see whether this image and this pin, they move together. They move together. If they move together, that means the image and the pin both are at the same line. They are on the same line. If they are on the same line, they will move together. What will happen if they are not aligned on the same line? When you shift your eye rightwards and leftwards, they will have relative motion. When one is going to the right, the other one is going to the left. When one is going to the left, other one will be going to the right. They will not be going together. The pins will not be, the tips of the pins will not be together always. When you are shifting your eye laterally, if the tip of the pin is being together, if both goes as same line, then we can say the position of the pin, position of the image, both are aligned. Until you get something like that, you have to change the position of this pin and get that particular state. What is the state? The image and the pin both move together as a single straight line, right? Once you have shifted like that, then we can say this is where the pin is. This is where the pin is. And that is what the image I is. Clear? In this situation of coincidence, when the eye of the observer is moved sideways on the axis, the tips of I and P should appear to move together without any relative motion. There should not be any relative motion. Now measure the distance U between the lens and the object and the distance V between the lens and the image using the meter ruler. By altering the object distance suitably, obtain 4 other pairs of readings U and V and record this reading in a table. Look at this. So this is the lens, this is the object. You can say this is the U, object distance. And since the image and the pin have coincided here, you can say this is the image distance. Now what you will do, shift this pin, move it further away from the lens, right? Change U appropriately. Every time you shift the U, the image's position also is going to change. Accordingly, you change the location of this pin, the pin that you use to find the position of the image, change that pin so that you can find the V. Then you will get multiple pairs of U and V values. We need at least 4 values, at least 4 points to draw a straight line. To draw a straight line, actually 2 points are enough, but in a practical there can be errors. When you do experiments, there can be errors. To make sure you get a closer to the precise answer, at least 4 points must be taken whenever you are drawing a straight line in an experiment. So change this U value at least 4 times, get different 4 values for U and the appropriate V values. Then what you do, take 1 over V in one axis, 1 over U in another axis, right? This is going to be in the x-axis, this is going to be in the y-axis. Why? U is what we are changing. U is the independent variable. So take 1 over U in the x-axis. We usually have a convention, independent variable must be taken in the x-axis. V depends on U. V depends on U, which means V is the dependent variable. Take 1 over V on the y-axis, draw the graph. We saw 1 over V equals 1 over U plus 1 over F. Then find the intercept, get the inverse of the intercept. That should give you the focal length of this particular lens. Shall we see how to do this experiment now? Hello students. In this experiment, what we are going to see is how to find the focal distance of a convex lens. So in theory, when we studied the theory, we studied a formula where the object distance U, the image distance V and the focal distance F are connected. 1 over U, 1 over V and 1 over F, we studied a formula between them. So using that formula, we are going to find the focal distance. So actually to find focal distance, you just need only one U value and one V value. Only one U value and one V value. But in physics experiments, we never conclude the answer with one reading only, because there can be errors when we do practicals. So what we do, we draw a graph. To draw a graph, we need multiple readings. At least 4 or 5 readings we take
for a straight line graph. So here also what we are going to do, we will take different object distances, and for those object distances we will measure the image distances, and then we will draw a graph against 1 over u and 1 over v. Using that graph, we will try to find the focal distance. This is what we are going to do in this experiment. So what is the title of this experiment? Finding the focal distance of a convex lens. First, let's see what materials and apparatus are required to do this experiment. So the instruments required to do this experiment. One, you need this lens. This is the lens of which the focal distance we are going to find. It is a convex lens. Then we usually have a bench like this. We call it lens bench. We can use this instrument to fix the lens, measure the distance, all that we can do with this bench. In case if you don't have this bench in your school, then you can just use this stand. This is a stand for the lens. So you can keep this stand and use the meter ruler to take the measurements. Right? If you don't have this bench, you can use this stand for the lens and you can use meter ruler to get the measurements. Here, since we have the bench, we will be using this bench. And these are the ones I am going to use. These nails are the ones I am going to use as object, and another nail will be used to match with the image. To locate the image, we will be using these two. And we have a screen. Why we get this screen is we will be fixing the screen behind all this, so that when we are looking at the image, when we are looking through the lens, we should not get interference from whatever we have behind this. So we will fix the screen here to ensure we don't get any interference. We fix the screen here to ensure we don't get any interference from the objects which are behind this. That's all the instruments we have, right? So now let's see how to do the experiment. So as I stated already, what we are going to do, we will keep the object behind the lens. We will be observing from here. This is where we are going to keep our eyes. We will be observing. In the middle, we will fix the lens, right? So behind the lens, we will fix the object. And we will get the real image of the object. If the object is kept beyond the focal point, then we will get a real image on this direction. So we will get the real image, we will locate the real image where it is. Then we can measure the object distance and the image distance. U and V can be measured. So you know 1 over U, 1 over V, 1 over F, we know the relationship. Then we can find the focal distance. So I'm going to measure different U's. That means the different object distances, and accordingly we will find the image distance. So let's fix the lens. We will not be moving the lens. We will keep the lens at one location. Let's fix it here. I may have to adjust the length later based on the object's height. We will have to adjust the height of this lens. So we'll just keep it. Let me fix it at 45. You can see here the scale we have, in the scale at point 45, at the scale 45, we will fix this. Right. So from 45, the object is going to be here. Suppose let's say I am keeping the object at 25. That means 45 to 25, my object distance will be 20. Suppose if I keep it at 15, 45, 15, the difference will be 30. So the object distance will be 30. That is how I will be changing the object distance, and we will measure the image or image distance. Right? Okay. And usually to draw a straight line, we need at least 4 points. Here we will take 5 points. We will take 4 points where the object distance is beyond the focal distance. And we will take one measurement, one object distance quite closer to this, such that it is closer or it is within the focal distance. You know, if it is within the focal distance, we will get a virtual image. So let's have a look at that also, how to locate the virtual images location. Right. So that's what we are going to do. So let's take 20 centimeter object distance, do the experiment, find out the image distance, and then we'll increase that by 5 centimeter by 5 centimeter. We'll take 20, 25, 30, 35. 4 different object distances, which we believe will be beyond the focal distance. Let's start with 20 centimeter object distance. This is at 45. If you want to have 20 centimeter, then the object has to be at 25 centimeters. I told you this is what we are going to use as the object. This is what we are going to use as the object. Yes. So let's fix it here. And I'm going to fix it at 25. That means this is at 45. The lens is at 45. If I fix the object at 25, then I can ensure this distance is 20. Let's check whether it is at 25. So let's fix it at 25. So I have kept the lens at 45, the object at 25, such that the object distance is 20 centimeter. You know, this is the object distance, the distance between lens and the object. Now from here I'm going to observe, let's keep a screen here to ensure I don't get any interference from anything behind this. For that purpose, sometimes they test this in the exam. Why do we use a screen here? So in this screen we are not going to project any images. This screen is kept just to get a clear vision of the image, nothing else. We are not projecting an image on the screen. There are some other experiments where we will use a screen and we will project the image on the screen. But here we are going to fix the image, fix the screen here only because we want to see the image clearly. We'll fix it here. Right, screen is fixed. Now, this is the important part of the experiment. See, I'll fix another nail here, right? And what I'm going to do here, from this side, I'll check the image of this. I can see when I look through this side, I can see the image of this object, which will be a real image. I might see somewhere here. In this side, I'll see the image. I have to align, I can adjust this, and I have to bring to a position where this one and the image of this object become collinear. That means they will be at the same line. Which means if I change my line of sight, I should see them moving together. They should not move relatively. There should not be any relative motion. I need to bring this one and the image of this one together in the same line. Until it becomes same line, until it moves like a single line, I have to adjust this one. The moment I get the image and this screw or this nail in the same line, then I can say that is where the image is. Image of this object is there. Right? So how we have to fix the nails? Usually the nails, this has to be a little taller. That means let me bring down this lens. Let's lower it. Okay, let's keep it here. And this nail has to be somewhere around the middle of this lens. So now it is too tall. We'll bring it shorter. Right. This is how we usually fix the nails, such that we fix the object and this nail such that we can see both the image as well as this one. Now let's observe from this side and see whether we can locate the image of the object. Remember, this is the object. This is a lens. I'm using this one just to locate the image. That's all. Let's see whether we can see the image. Now, there is another thing I have to tell you. If you keep this object too high, still you will see the image here, but it's better if you keep these screws somewhere in the middle of this line so that the threads could be seen. Because you will see an inverted image. So if you keep this, threads to be aligned with middle of the lens, when you see the image on the other side, you will see an inverted image such that the threads here would be seen again somewhere in the middle. So you will see the image like this. It will be easy for you to align the image and this nail, right? So I have kept it like that. The height of this is such that the threads are aligned with the midline of this lens. Similarly, the screw here, the nail here also I have kept it in the same height. Now let's observe again. I can see the two images. I can see the two images now, but they have relative motion. Like when I am shifting my eyes, when I am changing my line of sight, they don't move together. They are moving relatively. They are not moving together. So what do? I will adjust this position of this nail until they become collinear. That means they move together. Right, students. So at this position, I can see the image and this one are aligned together. That means the object here and the inverted image of this, the real image, the inverted image, they are together. When I change my line of sight, they move like this. They move together, which means this is where the image has to be. So I can measure the distance between the lens and the image. That will give me the image distance, which we mark by V. But you need to understand one thing. Object distance is in one direction. From lens, it is in one direction. The image distance is in another direction. So if I take this as plus, this has to be minus. Right? Anyway, when I am writing down these values, I will just write the distance only. When I do the calculations, when I do the graph, I will take with the sign. Understand? So the distance here, let me get the reading here. Find the reading we are getting. You can see here the line, this line, right? We have a line marked here. This line is exactly at 66 centimeters. 66 centimeters. You know, lens is kept at 45 centimeter. Lens is kept at 45 centimeter. So the gap between these two, 45 to 66, 21 centimeter, this gap. 21 centimeter. That is what the image distance will be. I took the object distance of 20 centimeter and I am getting 21 centimeter image distance. But mind you that one has to be plus. If I take the object distance as plus, this has to be minus. Because opposite directions we are measuring them. Opposite directions. This is plus, this is minus. Plus, minus. So when you are drawing the graph, we have to take care of those signs. For the moment, let's write down the distance we have got. U is 20 and V is 21 centimeter. So the object distance U, we have got 20 centimeters, 20. And V, we have got 21. Remember, I am not marking the signs. It was in the opposite direction. So actually, it has to be minus 21. But at this point, I am just marking the distance only. But when I am drawing the graph, I will take care of all the signs. 21 centimeter. 21 centimeter. Now what we will do, let's increase the object distance by 5 centimeter. That means we will make it 25 centimeter and see where the image is. So the next object distance we have to take is 25 centimeter. Remember, lens is fixed at 45. So if you need 25 centimeters on this direction, 45 minus 25, I need to fix the object at 20 centimeter mark here. Let's shift it to 20 centimeter mark. 20 centimeter. The object is at 20 centimeter. I have to tell you another thing. If you don't have this bench, if you are doing this experiment with the lens stand, then what you can usually do in a lab, you draw a line with chalk. Then Mark different lines at 5 centimeter gaps from the lens. 20 centimeter, 25 centimeter, 30, 35, 40. Likewise, you mark different lines in advance. Then what you do, first you keep the object like there. Object also can be kept on a stand. Then shift the stand from first line to second line to third line. Likewise, when you shift the stand, that means your object distance is changing. That is what you do if you don't have this bench. Right? Okay. Now I have kept the object at 25 centimeter gap. 25 centimeter gap. That means U is 25 centimeter. Let's see where the image is going to be. It's the same process again. I'll be observing from this side. And change the position of this one until I see the image, the inverted real image of this object, and this nail become collinear. They have to move in the same line. Shall we see how to get it? Right, students. So at this position, we have got the inverted image of this object and this nail being aligned. That means when I change my line of sight, both of them move together. There is no relative motion, which means the image of this object has to be at the same point here. Clear? Right. Now let's get the reading. Reading means, you know, the lens is already fixed at 45 centimeter. I need to get the reading here. Then the difference has to be the image distance. Let's get the reading here. You get 61.5 centimeter. 61.5 centimeter reading here. Can you see that? 61.5. This is already at 45. The difference between 45 and 61.5 is 16.5 centimeter. This difference. 16.5 centimeter. This 16.5 centimeter will be the image distance. Distance of the image from the lens. 16.5 centimeter. Right? We took 25 centimeter object distance. For 25 centimeter object distance, on the other side of the lens, we are getting 16.5 centimeter image distance. Shall we write it down on our table? This time the object distance we took 25 centimeter, and the image distance we have got 16.5 centimeter. Remember, it's a minus 16.5. For the moment, I am writing it as 16.5. When I am drawing the graph, I have to take care of that sign as well. Now, I have taken 20 centimeter, 25 centimeter. Next, we take 30 centimeter object distance and find out where the image is. So, the next object distance we have to take is 30 centimeter. This is at 45. You need 30 centimeter. That means the object has to be shifted to 15 centimeter mark. 15 centimeter mark. Right. Let's repeat the process now. Object is at 15 centimeter. That means you have a gap of 30 centimeter. 30 centimeter is your object distance. Now we'll locate where the image is. So you move this nail back and front to find out where exactly it becomes collinear with the image. So students, at this position of this nail, the image and this nail became collinear. So let's measure the image distance from the lens. Lens is at 45 centimeter. Image is at, you can see it's at 60.4 centimeter. 60.4. So 45, 60.4 means 15.4 centimeter is the image distance you are getting. 15.4 centimeter. Let's write it down on our table. U 30, V 15.4 centimeter. U 30 centimeter, 30. And V, we have got 15.4 centimeter. 15.4 centimeter. We have taken 20, 25, 30. Let's take another one beyond 30, maybe 35 centimeter we can consider. After taking those four, let's take another point very close to the lens such that it is within the focal point. Let's change the object distance this time to 35 centimeter. 45 less 35, it has to be at 10 centimeter mark. Shift it to 10 centimeter. 10 centimeter mark, which means 35 centimeter is our object distance we are getting. Let's measure the image distance. For that, let me move this and coincide with the image. So at this position, we get the image and this nail are collinear. Get the reading here. You can see it's at 59.8 centimeter. 59.8 centimeter. This is at 45. This is at 59.8. That means 14.8 centimeter. We are getting 14.8 centimeter. 14.8 centimeter is the image distance. Let's mark that also on our table. U 35 centimeter, object distance 35 centimeter, and V we have got 14.8 centimeter. 14.8 centimeter. I have taken 4 readings beyond the focal point. This is good enough to draw the diagram, draw the graph. This is good enough to draw the graph. Let me take another point within the focal distance. Maybe we can take around 8 centimeter. So how do we know when you shift that within the focal distance? You know, if the object is beyond the focal distance, you will see an inverted real image. But when you bring it within the focal distance, you will not see an inverted image, you will see an erect image, right? So let's see whether that happens. So we have to bring the object within the focal distance. Let's bring it somewhere around 8 centimeter. But how do we confirm that 8 centimeter is within the focal distance? You will not see an inverted image, you will see an erect image. That also will be an enlarged erect image behind the object you will see. So let's bring it close to the lens. Maybe 8 centimeter we can try. 8 means this is at 45. 45 minus 8, 37. Let's fix it at 37 centimeter. Also, I'm going to do one more thing. I'm going to raise this object because I want to see the image of that in the full length. So let's raise it. And fix it at 37 centimeter so that the object distance is 8 centimeter. All what I'm going to see from this end when I look at it, now the object distance is 8 centimeter. 45 and 37, the gap is 8 centimeter. When I look from this end, if I see an erect image, not an inverted image, if I see an erect image, that confirms that the object is within the focal distance. Let's see whether I'm seeing an erect image. Yes, I can see an enlarged erect image of this object, which ensures the object is within the focal distance, which means the image of this object is going to be behind this. So let's fix another nail here to align with the image. And how I'm going to align it? The nail I fix here, I have to see above the lens. And the image of this I have to see within the lens. Nail above the lens, image within the lens, both have to move collinearly. Because of that, I need a lengthy nail here. Let's use a nail like this. We can use this. Yes, a lengthy one. Let me fix it here. I must be able to see this above the lens, and I don't need this anymore. This can be removed. I don't need this anymore because this is the object. Lens is going to be behind this. I don't need this. We can remove it. The image and this nail are not moving collinearly. There is a relative motion between them, relative motion. So I have to adjust this and find out where they coincide. That means they move together. When I change my line of sight, they should move together on a single straight line. Let's see where that happens. Now students, you can see this is the image. This is the image. You can see the image. And this is the nail behind that. Now this image and this nail, this image and this nail have to be collinear. Let me change my line of sight and see whether they are moving as a single line. No, you can see there is a relative motion. They are not moving together. There is a relative motion. So let me change the position of nail until it becomes collinear with the image. Still you can see there is a relative motion. It's not perfectly coinciding. It's not perfectly coinciding. Not yet. Not yet. At this point you can see the image, that means this image and this line both move together. They move like single line. You can see when I change my line of sight, there is no relative motion between this image and this line. So this explains us where the image is located. Let's see how to get the reading. At this point I can see the image of this object. That means an erect, enlarged image of this object and this nail, they are collinear, they coincide. Which means the image of this object is exactly where, exactly at the same point where this nail is. If I measure this distance, the distance between lens and this nail, that would give me the image distance. Be careful, this last one we are taking, since we kept the object within the focal distance, we are getting the image also on the same side. So the sign of u and v are going to be same. We are measuring in the same direction. For the previous 4 readings, I told you, u is in one direction, v is in the other direction. If u is plus, v has to be minus. But this time, if u is plus, v is also plus. Even though we are just writing the distance now, when we draw the graph, we have to take care of this. The last one I am taking 8 centimeter object distance. The image distance is going to be in the same sign of u. If u is plus, v is also plus. Let's get the reading. You can see here, the mark is at 5.3 centimeter, 5.3. And length is at 45, we already fixed it. 45, 5.3, the difference is 39.7 centimeters. 45, 5.3, the difference is 39.7 centimeters. So the image distance we are getting 39.7 centimeter on the same side of u. If u is plus, this is also plus. So plus 8 centimeter plus 39.7 centimeter. Let's write this value as well on our table. When we are drawing the graph, we have to be careful. The first 4 v's were in the opposite direction to u. So if I took the u values as plus, v should have been minus for the first 4. But the last one, if u is plus, v is also plus because we got it on the same direction. Now let's see, we have to mark all these on a graph sheet, draw the graph and see how we can get the focal distance of this convex lens.
Students, you can see I have tabled all the values we have got. This is u and v. V I have given certain values minus, certain values plus. The reason is this. Look at this. When we kept the lens here and the object is in one direction, one side of the lens, image is on the other side. U measured in this direction, v on the other direction. We took u plus, v minus. First 4 cases, this was the situation. We got real image on the other side of the lens. The last one, what did we do? We kept the object closer to the lens, which means within the focal length, so that we got the virtual image behind the object on the same side of the lens. U, v both are measured in the same direction, so u and v both will be plus for the last one, right? Now what we are going to do, we are going to take this in the x-axis, take these values in the y-axis, draw a graph and see whether we get a straight line. What do we want from the graph? We want the intercept of the graph. Let's see, have to plan the scales properly. I have taken a graph sheet where I have 35 segments here, 35, and 18 segments in the vertical side. How I am going to take the scale? Look at this. Let me draw the y-axis, which is 1 over v, centimeter minus 1. Let me take 0 here and take this as 0.02. That means each subsection I am taking as, each section I am taking as 0.01. Then this will be minus 0.02. This will be minus 0.04. Minus 0.06, minus 0.08, minus 0.10, minus 0.12. That's how the y-axis scale will be. X-axis, this is where I have taken 0 of the y-axis. So x-axis is going to be like this. 1 over u, centimeter minus 1. The scale I have to take, you can look at the x-axis. I have as low as 0.0286, maximum 0.1250. what we will do, 2, 3, 4, 5 sections, I will mark it as 0.02. 1, 2, 3, 4, 5 sections, another 0.02. 3, 4, 5, 3, 4, 5, 0.06, 3, 4, 5, 0.08, 3, 4, 5, 0.10, 3, 4, 5, 0.12, 3, 4, 5, 0.14. Right? Let's mark all the points that we have taken. First point, 0.05 and 0.0476. So let's say 50 and 47.6. 50 has to be right middle here. 47.6 in minus 40, 50, 47.6 will be here. 50, 47.6. 40, 60.6. 40, 60.6. 40 is here, minus 60.6. 60.6. Almost here. 33 and 64.9. 33. This is 20, 24, 28, 32. 32, this is 36. 33 must be somewhere here. 33 and 33.3 and 64.9. 64.9 you will have 60. This was 70. 64.9 is somewhere in the middle. That's how we are getting that point. Fourth one. Fourth. 28.6, 67.6. 28.6 here. 67.6. 67.6 here. And the last one, 12.5 and 2.52, or 125 and 25.2. 125 has to be here, and 125, 124, 125, yes, and 25.2, 25.2. This is 20, this is 30, so 25.2 has to be here, a bit above that. Right, those are the 5 points we have got. You remember I told you earlier also, when you do an experiment, there can be errors in the experiment. You won't get precisely like you are getting in a theoretical calculation and graph. So the lines, the points we get might not exactly fall on a straight line. There might be a little bit of deviations because practical errors are there. What we think as the perfect coincidence may not be the perfect coincidence. When we think the image and the pin are moving together, still there might have been a small relative motion which we did not notice, which we could not notice. Right? Because of those reasons, there might be small errors. Now with all 5 points, let's draw the best line that we can draw. Maybe let me start from here and see whether I can cover most of the points. Yes, a graph like this seems a good graph. Can you see 3 points out of the 5 points are on the graph? 1 point is a little bit deviated downwards. 1 is little bit deviated upwards. This is the best line we can draw from this graph, right? From the graph, see, when you are drawing the graph, what you must be careful, make sure you mark the axis. Independent variable on the x-axis. So u is the independent variable. We need 1 by u. Mark it on the x-axis with its unit. With its unit. And in the y-axis, it has to be dependent variable 1 by v with its unit. And what we need from this graph mainly, we want to find the focal length. To find the focal length, I need the intercept. Look at the intercept here. Look at the intercept here. We get the intercept at minus 0.10. Minus 0.10. Let's do the calculation. Intercept. The formula we had 1 over v equals 1 over u plus 1 over f. Y equals m is 1. X plus c. Intercept 1 over f, which is what we measured as 0.1, but minus 0.1. Minus 0.1. From this you will get f equals 1 over minus 0.1, which is minus 10 centimeter. We studied in theory according to Cartesian convention that the focal length of a convex lens has to be minus. Yes, we are getting minus 10 centimeter. Is that clear? So this is what the simple experiment it is. First understand the concept, what we are trying to do. After understanding the concept, then look at the methodology. What steps we went through in doing the experiment. Right? You can't just memorize and go, because if we just memorize and go, you wouldn't understand the practical problems we face when doing the experiments. When they test this in the exam, they mainly ask questions about, practicalities. That's why they call it practical experiments. If you do it only, you will understand why we have a screen there. What are the problems? Why do we sometimes get the image and the pin that we kept, they are not on the same straight line? What could be the reasons for that? Now, these are the questions they ask. Either you have to do this experiment yourself. If not, you have to watch. When I was doing it, you have to watch it a couple of times again and again to understand each and every adjustment we have done in this experiment. Clear? So, I believe that was clear to you. Before we go to the next experiment, what is going to be the next experiment? Finding the focal length of a concave lens. This is convex lens, concave lens. But before that, we will see what past paper questions we can do for this experiment. Okay, first I have taken a question from 2004 advanced level paper. Figure 1 shows a schematic diagram of a properly arranged experimental setup used by a student to determine the focal length of a convex lens L. In this experiment, the position of the real image of pin X is found with the help of pin Y. So, understand this is what the object pin is. This is the screen. Lens is here. He is going to move this pin, forward and backward to locate the image of X. This is where his eye is going to be E. What is the advantage of having the screen S? What is the advantage? To avoid interruption from the other objects. To avoid seeing other objects. You can say like that, or you can say to avoid interruptions from other objects, or you can say to see the image clearly. Yeah, whatever. Figure 2 shows the field of view with the pin Y that the student sees when he keeps his eye at point E on the principal axis of the lens to observe the real image of X. The image of X is not shown. Draw the image of X on figure 2. So, what you see here, this is pin Y, right? Image of X has to be an inverted image, right? Inverted image. So, how would that be? It has to be collinear with this. That's how you will get image of X. Image of X. Next, if the student moves his eye sideways, observing the movements of Y and the image of X, what will he see when the image of X is not formed at the position of Y? If they are not at the same position, what will happen? There will be a relative movement. There will be a relative movement. Relative movement between Y and image of X. The image of X is formed at the position of Y. When they are at the same location, same position, what will happen? Both will move together. Both will move together. No relative motion. No relative motion. These are the exact terms we studied. These are the exact terms I have shown you in the experiment. You have no complication answering questions like this. Write down the relationship among the object distance u, image distance v, and the focal length of f, the length for this experiment after applying the sign convention to the length equation. After applying the sign convention to the equation. See, there are two approaches. One is apply the sign convention in advance. Then the numbers you substitute, you can just put the numbers only. U, V, the measurements you got, you don't have to worry plus minus, just substitute the number only. Or else keep the original formula 1 over V minus 1 over U. Just keep it as it is. When you are substituting the numbers, check the convention plus minus and accordingly you can substitute. Here what they ask, they want you to change the equation itself with the sign convention. So, let me write the original equation first. 1 over V minus 1 over U equals 1 over F. If I apply the sign convention for this, U will be plus, V will be minus, right? And F also minus. If I apply this sign convention, what will happen? V is minus. You will get minus 1 over V. U is plus, but already a minus was there. Minus U remains as U itself. F has to be minus 1 over F. Since all are minus, you can leave them. 1 over V plus 1 over U. 1 over U equals 1 over F. This will be the formula for a convex lens after you applied the sign convention into the formula itself. Next. The student recorded U and V in centimeter and plotted the graph shown with properly selected axis to determine the focal length of the lens. Note that the student used the values recorded in centimeter to draw the graph. Okay. He has got 5 points. Good. Let's see what they ask. Label the axis of the graph. Label the axis. So, this has to be 1 over U centimeter minus 1. This has to be 1 over V centimeter minus 1. Determine the focal length of lens L. The formula that we are using now, 1 over V plus 1 over U equals 1 over F. 1 over V will be minus 1 over U plus 1 over F. Y, M, X, C. This time M is minus 1. That's why the graph is going to be downwards graph. Downward sloping graph because the gradient is minus. Let me draw the graph. We get a graph like this. Look at this. 0.1 on this side, 0.1 on this side also. Because the gradient has to be 1 in magnitude. Magnitude of the gradient has to be 1. Yes, you get same distance on both sides. Since it is downward sloping, it has to be minus. Minus 1. Fine. But what we need more importantly is the intercept. Find the intercept. It's 0.1 here. So I can say 1 over F equals 0.1. From this you get F equals 10. 1 by 0.1, 10. Careful, this is in centimeters. 10 centimeter. All the measurements were in centimeter. When you find the focal length also, you have to give it in the right unit, centimeters. For a certain position of X, a virtual image is observed by the student. He decided to find the position of this virtual image using a plane mirror. He is using a mirror to find it. I'll show you how to use a mirror. By drawing in figure 1, show how he should place the plane mirror and the pin Y for this. Label the plane mirror as M and the new position of Y as Y dash. Look at this. Now, first we'll understand where the image of X is going to be. They say this is within the focal length, right? Then understand somewhere like this only you are going to have the image of X. They did not ask you to draw the image of X. Anyway, for you to understand, I am drawing this. In the exam, you don't necessarily have to draw this image of X. Then what will happen? This is the plan. Look at this. Keep a mirror here. Don't cover the entire lens. Just cover part of it. Approximately half of the lens has to be covered by the mirror. And keep Y inverted. keep y here. Now this is the new position of y. Let me mark it as y dash. What's the plan? What's the plan? When you look from here, through this mirror, you will see the image of this y. That will be in the same size of y, in the same orientation of y. You will see behind the mirror such that object distance and image distance are same. So if you have it here in this much of distance, in the same distance behind the mirror, you will see the image of y. Right? At the same time, when you look through the mirror lens, you will see the image of x, a virtual image of x as well. Now what we are trying to do, we are trying to coincide both images. Which images? The virtual image of x, the virtual image of y, both we are going to coincide. See, when you are looking from here, you are going to look through the mirror and the lens simultaneously. At the same time, you are looking through the mirror as well as lens. Through the mirror, you will see the image of y. Since I kept y inverted, similarly an inverted image you will see. Since the object is inverted, image is also inverted, nothing else. The mirror doesn't invert it. Since the object is inverted, the image is also inverted. Right. So you will see the image of y in the same size in such that object distance and image distance are same. You will see that. Also, you are going to see the image of x, virtual image of x, because you have kept x within the focal length of the lens. You can adjust this y such that both images coincide. Right? That's what you have to do. But then, okay, if I go a little further, how are we going to measure the distance? Listen. See what I am writing with this color, you don't need to write it in this exam because they didn't ask you that. Now imagine at the point of coincidence, this is where y's image is going to be. Y's image. Both are coinciding, right? Image of x, image of y are coinciding. If I mark this distance as x, this also has to be x, correct? Why? From the mirror, the distance to the object, distance to the image has to be same. You can measure this one. The distance between lens and the mirror, you can keep a meter ruler and find it. Now, image of x from the lens, this has to be the distance, right? V. And this is u. You can just measure it, but v will be x minus y. Look at this. From this, how do you measure x? You don't have to measure the distance of image, but you can measure the distance of the object, right? From the mirror, the distance to the object you can measure. You can use a meter ruler and measure it. That's going to be the same distance to the image as well. So this is x, but you measure this one. And then you measure y. X minus y is going to be v. You can measure. Understand? This is how, using a mirror, if you want to find the virtual images distance, we do it. Clear? The last question, you have to think a little bit. I would say nothing new in this question. You know why? This is a similar approach we will be using in concave lenses experiment. So when you go to the exam, you have already done the convex lens, you have already done the concave lens. So you know this. You know this. This is nothing new for you. Anyway, put a star for this. This is a new thing that they have asked. Shall we go to another question now? 2012 question. You are asked to verify the length formula by plotting a suitable graph and to determine the focal length of a convex lens. A partly assembled setup that can be used for this purpose is shown in the following diagram. U is the object distance. You are provided with an object pin P, length L, locating pins P1 and must be P2 and P3. Yeah? P2 and P3. This is P1. One short and other tall. Look at P2 and P3. One is a shorter one. P3 is a taller one. And a white screen S. This is a white screen, the background screen. Considering two light rays coming from point X marked on P1, draw a suitable ray diagram to locate the image of the object in P1. Draw one line through the optical center of the lens so that it doesn't deviate. It's easy for you. Draw another line, maybe a parallel line that goes through the focal point. A parallel line that goes through the focal point. Clear? Next one. Or maybe you can draw another one, a line going through the focal point. If it goes through the focal point, then it has to be parallel on the other side. It has to be parallel on the other side. If you can draw that also. They ask you only 2 lines. This is enough. Draw the screen S at an appropriate place in the above diagram. Okay. So this is where the object is, right, outside the focal point. So you will be seeing a image on the other side. This is where you are going to keep your eye, which means the image, the screen has to be behind the object also. Screen has to be behind the object. That will be the screen S. What is the purpose of keeping S at the place where you have drawn it? Same question they asked in the previous paper as well. To see the images clearly. To see the image clearly. Without interruption from other objects. Without interruptions from other objects. To determine the image distance V of the object pin P1, the locating pin P2 has to be used and you have to place your eye at a suitable position. Label this position as E in the above diagram. We already marked it. We'll just name it as E. E. This is where you're going to keep your eye. How do you make sure that the image of P1 coincides with P2? What do we do? Move your eye sidewards and see whether both are moving together without relative motion, right? Move the eye sidewards. And change the position of P2 until P2 and image of P1 move together without relative motion. Move together without relative motion. Clear? We have done that many times. You know that very clearly. Next. Suppose you want to take a few readings with virtual images too. Draw the object pin and the locating pin at appropriate places for taking such a reading and label them as P1, P2 or P3 in the following diagram. Positioning them at exact location is not necessary. Okay. Let's say this is where you want to keep the pin because you have to keep it within the focal point. Then you have to keep a longer pin, the taller pin as the locating pin. P1 has to be kept here. P3 has to be kept here. P3 has to be kept here. In the previous one, did they ask us to mark pins? No, they asked us to mark only S. They asked us to mark only S. Yeah, P1. And then they asked us to mark S, draw the screen S. Then they asked where you would keep your eye. P1, the locating pin P2 has to be used and you have to place your eye at a suitable position. Label the position as E in the above diagram. Let's mark P2 also there. Where would you keep the locating pin P2? Somewhere here. P2. So when you keep P2 here, P2 doesn't have to be taller than P1. You can keep a similar sized one. But to locate a virtual image, you have to have a taller one. Why? When you look from here, through the lens, you will see the image of this pin. And outside the lens, you will be seeing this pin. what you see outside the lens and what you see inside the lens have to move together. Draw a graph that you would expect to obtain on the following grid. Your graph must contain data points for real images as well as virtual images. Label the axis. Right. So this is 1 over V, maybe we can say centimeter minus 1 over U, centimeter minus 1. This is the same graph that we drew in our experiment. A graph like this. A graph like this. So where will you have the real images? When U is plus, if V is minus, this is real images. When U is plus, V is also plus, that is for virtual images. Virtual images. What is the expected gradient of the graph? Gradient has to be plus 1. Plus 1. How do you determine the focal length? We have done that in our experiment. F will be 1 over intercept, the inverse of intercept. Correct? A student says that in the case of real images, when one pair of U and V values are obtained, 2 data points could be plotted on the graph. Would you agree with this? Give reasons for your answer. Now look at this. When lens is kept like this, if this is your object and if you are getting the image here, when this is the object, if this is the image, you can interchange these two such that if this becomes the object, this will be the image. Right? When you get real image on a convex lens, the position of image and object can be interchanged. Imagine, originally this would be the U and this would be the V. From the lens to the object U to the image V. When you interchange these two, now this will become U. Previous V is going to be U now. Previous U will become the V. Understand? So, interchange, because you know, after we applied the sign convention, we saw in the 2004 question, 1 over U plus 1 over V equals 1 over F. 1 over F. Right? So, imagine if U and V are interchanged, there is no change happening on this side, right? If I put V here and U here, doesn't make any difference. Do you understand? So, if you take one pair of value for U and V, let's say when U was 10 centimeter, let's say when U is 10, V was 20, let's say. If that is the case, later if U becomes 20, V will be 10. When U becomes 20, V will be 10. Understand? So, you can interchange U and V. That's what he says in this particular statement. So, you can say, yes, I agree. Yes, when convex lens produces real image, the object and image can be interchanged. That is, U and V can be interchanged. So, if you measure one U and V, actually you can take it as 2 separate points. You interchange the UV values, but understand this is only for real image scenario, not for a virtual image scenario. That's what we got in this paper, 2012 paper. All the questions were easy. Last one is the only one. Every paper, every question, the last one they will have a little bit to think. Right? Previous all of that, it's very easy, straightforward. Let's see one more question on the same experiment. 2015 one. You are asked to determine the focal length of a convex lens experimentally using the no parallax method. No parallax method is where we coincide the image. Yes. Assume that you are provided with all the items necessary to carry out the experiment. Draw a diagram to show how you would set up all the necessary items on the table to carry out this experiment and label the items. Stands on which the items are mounted should be clearly drawn. If you have done the 2012 paper, this is easy because there every diagram was very clear. Right? Let's say this is the principal axis. That would be the stand. Let's draw the table also. This is the table. Right, that's our lens. Let's mark it as L. And then you will keep the object. You have to keep a screen here. Screen with a stand. Screen. You have to keep another object here. Another pin here. You can call it locating pin. Did they give name for that? No. Locating pin. Let's name it lens. Object pin. Object pin. Screen. Right. So make sure you show the stand and the pin. Stand and the pin. Stand and the lens. Because they asked you to draw with the stand. Next. Before setting up the items of the experiment, it is convenient to know a certain data pertaining to a certain item given. What is this data? Describe a simple method to obtain an approximate value for this data. When I was doing the concept, I explained you get the parallel rays on the lens, converge them at a point, find the distance between the convergent point and the optical center of the lens. That will give you approximate focal length. So let's write it. What is this data? Approximate focal length of the lens. Describe a simple method to obtain an approximate value. How do we do it? Get the image of a distant object on a screen. Get the distance between the screen and the optical center of the lens. That will give you the approximate focal length. Next, suppose that when looking at the image after setting up all the items as indicated in A, you have observed that image and the observation pin are not in the same vertical line. Give two reasons, one related to the pins and the other related to the lens as to why this has happened. Why this problem happens? I told you there are two reasons. One, pins are not kept on the same line. Lens is not perpendicular to the line. Let's say pins are not kept on the same line. Hope you understand what he is talking about. Right? If this is the field of view, sometimes you will see your locating pin like this and the image of the object pin like this. They are not on the same vertical line. See, when you are looking at the primary axis, principal axis, they have to be at the same line. Whether they have been coincided or not doesn't matter, because where you will see the relative movement is when you move your eye sideways. When you look at the principal axis, whether they are aligned or not, whether they are coincided or not, they must be at the same line. They must be on the same vertical line. If they are not on the same vertical line, there can be two reasons. One is the line, the horizontal line you have drawn, or you can say the principal axis and the lengths, the line and the length are not perpendicular. You did not keep the lengths perpendicularly, or else you did not keep the pins on the same line. Right. So that's what I'm telling here. Pins are not kept on the same line. Lengths not perpendicular to the line. To the line. Next. Which line? Where you have, see, like one pin, the object pin, locating pin, you connect those two with the line. Right? If you have kept them on the same line, then the lengths have to be right perpendicular to that, right normal to that. If it is not normal, then you won't get them. You will get something like this. Next. In this experiment, suppose you have observed that as the eye is moved sideways across the optical axis, the image moves opposite to the direction of the eye movement. In this situation, state whether the observation pin should be moved towards the eye or away from the eye in order to locate the exact position of the image. See, if it is moving in the opposite direction, you must take your locating pin towards the eye, Then only you can coincide the image and the pin towards the eye. In the object distance, image distance and focal length of the convex lens are u, v and f respectively. Rearrange the lens formula in order to determine the focal length of the lens by plotting a linear graph. 1 over v minus 1 over u equals 1 over f. 1 over v equals 1 over u minus 1 over f plus 1 over f. This will be y, x, c. Y equals mx plus c. What's the sign convention? We'll use Cartesian convention. Right? That will be the Cartesian convention. Next, or you can even say the standard convention or Cartesian convention. Mark the independent variable of the equation obtained above in the horizontal axis. 1 by x, 1 by u, centimeter minus 1, 1 by v, centimeter minus 1. And the dependent variable on the vertical axis. Draw a rough sketch of the expected graph on the same diagram. Use the signs for the object distance and image distance according to the sign convention. This is how the graph is going to be. You know, this is where you get the real image. This is where you get the virtual image. That means u, v both are plus, that will be virtual image. U is plus, v is minus, that means that's real image. Clear? Quite simple experiment. I have shown you 3 past paper questions, quite frequently tested. You saw that 2004, 2012, 2015. There are many more questions as well. I just took only 3 questions for you to revise. So go through all these questions. You will understand how easy it is if you have gone through the experiment carefully. Clear? Now, once you practice all this, come back. We will see the next experiment. What is going to be the next experiment? Finding the focal length of a concave lens. This is for convex lens we have done. We will see that for concave lens.